Populating our framework with particles, many effects can emerge. Locality from recursiveness makes possible distance and velocity. Particles can affect each other with waves. This radiation has a finite constant speed of propagation, so particles can also use waves to quantify velocity and distances. Locality of each particles create an exclusive space that allows for collisions thanks to the relative velocity. Particles are also the fundamental element for all transformations of energy. They can absorb radiation, convert some into motion, but it can also emit as well deflect waves. Inertia of particles becomes evident with relativity. Along with the momentum emerges conservation. Whatever velocity I observe, including no apparent movement, it is conserved thanks to inertia. Collisions are capable of transferring momentum, and here we also have kinetic energy. The relative velocity between colliding systems is one of the key factors determining the amount of energy that is involved, and also affects the results of the interaction. Each fundamental system possesses one of the two possible electric charges. This charge is measurable through the field addressing the particle, since fields allows for the interaction beyond the reach of particles' locality and collision. The electron behavior is dualistic, based on repulsion or attraction according to charge and distance. From the dualism of charges originates the Coulomb force and, more in general, the whole electromagnetism. All these properties and effects emerge with particles. They don't exist among waves. They are always particle dependent. It is also pretty clear that a model incapable of telling the two apart must be wrong. On macroscopic scale, with plenty of these systems, we have even more emerging features. But first, we talked about transformations of energy, and we must pay attention to conservations. Fundamental particles have a stable ground state, meaning there exists a minimum amount of energy in this locality, below which the particle will never go. The ground state may vary, in any case, it is a long-term stable condition. The particle can't lose all of its energy, and we usually refer to this value as the inertial mass. Particle in ground state is some amount of standing energy that cannot evaporate, neither is easy to break apart. The unitarity of fundamental particles seems tightly related to the conservation of charge. The charge is against a complete decay into free propagating wave, since no charge can disappear without its antiparticle. We can count particles using charge, and along with it, the particle in ground state is conserving energy and all of its properties. It follows that a particle cannot violate locality, and it is very different from a free propagating wave because of its very distinctive features. There can be fluctuations between free propagating waves and particles. No spontaneous pendulum can continuously make disappear and reappear locality, charge, inertia, or so. The reason is pretty straightforward. In the instant a particle becomes a free propagating wave, it's in the same annihilation condition, so the energy disperses. Particles can receive energy in many ways and exist above their ground state, but the system will emit the exceeding energy to spontaneously decay toward its ground state. Once again, almost all these properties and effects do not exist in waves, marking the distinguishing features of particles.